Hi, my name is David Chandler. I've taught high school and junior college level physics and math from 1972 to 2012, except for a couple years in the middle where I worked as a computer programmer. I've taught in public and private and international schools. In the last 9 years of my career, I was at a charter school that worked with homeschool families. That experience led me to recognize the need for a high-quality math curriculum that was accessible to homeschoolers, that didn't water down the math. You don't make math easier by watering it down. You make it easier by explaining it clearly. So starting in 2006, I took it as a goal to record the entire high school math curriculum in a format that was useful for homeschoolers. And over this last year and a half, I've added a physics course. Physics is my real thing. I have a bachelor's degree in physics and a master's degree in math, but I teach mathematics from a physicist's point of view. I see math as a powerful tool for both creativity and for understanding the physical world. One of the perennial questions you get, every math teacher has heard this 1,000 times, when are we ever going to use this? You may have heard that question yourself. My short answer is, take physics. Physics is not the only place where you're going to use high school level math, but it's one place where you're going to use basically all of it. Physics isn't a math course, but it uses math as a tool. One of the big differences in teaching physics and math is in physics, you really need labs, and that's because you need to experience and analyze the phenomena of the real world. Taking physics along with the appropriate level of math not only helps you do the physics because you're learning the tools of the trade, but it helps you with the math because it gives a context for what you're learning there. It's no longer just a random collection of techniques learned in the abstract. So I thought what I would do today is walk through some of the big ideas introduced in the high school math curriculum and show you some examples of where they show up in the context of physics. Okay, let's start with a linear function. It's something that looks like this: y equals something x plus something. These can be any two numbers. This one's considered to be a constant because it's just a number with no variables. This is called a coefficient of x, and this is your linear term and your constant term, and that's it. No other terms. So as long as you have an equation that looks like this, if you graph it, it's going to be a straight line. You may have seen this in algebra with labels here like m and b, y equals mx plus b. That's just sort of a convention. The m and the b are just labels for these two numbers. But anytime you have an equation with this kind of a pattern, you can tell right off the bat it's going to be a straight line. Let's play with this in GeoGebra a little bit and get a feel for it. Okay, here we have a linear equation down here, a linear function, y equals mx plus b. And here I have the equation with values plugged in. And right now they're both ones. I have little sliders here so we can change the value for the m and the b. Notice what happens when I change m. The effect of that number, the x coefficient, is to change the slope. And look at this. If I change b, it pushes the whole thing up and down. And in fact, b is the place where this line is going to cross the y-axis. So it's frequently just called the y-intercept. So there you have it. Here's a straight line, and this number gives you the slope, and this gives you the y-intercept. This is all things you would encounter in your Algebra 1 class. Okay, here I have a little battery-operated car, and I just hit the switch, and it travels across the floor at a constant speed. Here I've imported that little video clip into a program called Tracker. It's a free download. You can get it off the internet, and my physics students all have this and use it. And now if I run the car here, notice I have a little marker that I've placed on the car in the same spot every time. And this is tracking x versus time. So this is where horizontally it is as a function of time. Okay, here I've brought the data from Tracker over into an accompanying program called the Data Tool. And if I choose a range of points here, I can fit a line to the data. And down here it gives the equation as AT plus B. That looks a lot like y equals mx plus b, where A is the slope and B is the intercept. And over here, you see the A says 3.24 whatever times e minus 1. That's times 10 to the minus 1. So it's 0.324 meters per second. We're actually getting the speed of the cart. So the slope of a graph like this actually represents the speed. Now let's come back to this and go one step further. What if I take y equals something x squared plus something x plus something? So if I go up to x squared terms and not just constants and x terms, this is called the constant term, the linear term, and this is called the quadratic term, and so this is now a quadratic function. Okay, what's going to happen now? Now again, these can just be designated by like A, B, and C, or any three letters like that, but it's really just three numbers that fit in here. Let's see what these do to this type of an equation. Okay, here's our quadratic function. And it looks just like the original straight line, and that's because the a here, that's this number in front of the x squared term, is 0. So that just makes this term drop out. And therefore all we have is the bx and the c. So if I vary the b and the c, it does the same thing that we're used to seeing. Okay. Well, what happens when I make a non-zero? Ta-da, there we go. Notice that that introduces curvature. And if I have a as positive, it curves up. And if it's negative, it goes down. If I change the b, notice it doesn't affect the curvature. Okay. And if I change the c, that pushes the whole thing up and down. So that's interesting. So this is a graphical way of understanding a quadratic function. But still, you might be wondering, when are we ever going to use this? What is this all about, really? Okay, here's a different kind of a cart. It has a spring, and as you pull it back, it loads the spring. And so it's being driven by a force. And I have a couple of masses taped onto this little cart here. And if I apply a force to a mass, it'll cause it to accelerate. And acceleration produces a different kind of motion. Notice it's picking up speed as it goes. Anytime you have a constant force acting on a mass, it's going to move in such a way that its position, measured relative to time, will come out a quadratic equation. Here I've brought the video clip into Tracker, and I have two weights taped on it, and I'm just going to run this and see how it looks. Okay, so I pull it back, loading the spring, release it, and start tracking. And notice that we have a graph that's curving upward, showing increase of motion as we go along. Okay, here I've brought the data over to the data tool, and instead of fitting a straight line to the data, let's fit a parabola. And so let's take a range of data here that's close to where it starts, and notice we have a pretty good parabolic fit up to a certain point. And that's because once the spring has expanded out, it's no longer exerting a push on the cart, and so it quits accelerating. So at least for a range of motion, it's accelerating, and we have a quadratic equation that would describe the motion. So what we say here is that we're modeling the motion using the equation. So the equation describes a certain range of the motion whenever the conditions are following our assumptions. So this is a common use of mathematics. You can't say that the whole world is following your equation, but the equations can describe at least bits and pieces of what we observe. Okay, projectile motion is a nice example of both linear and quadratic equations, because what we have is a two-dimensional motion. Horizontally, there are no forces acting apart from air resistance, But vertically, there's a uniform force acting, namely gravity, which is straight down all the time. So if I look at this separately in terms of x and y, this particular graph is showing y versus t. Let's run the video here. So if I let it go, I'm tracking just the top edge of the ball to have a nice sharp thing to track there. But notice we see a parabola here, and this is not a picture of the motion. It's not x versus y, it's y versus time. So this is the height of the ball as a function of time. If I come back and look at the horizontal position, let's do that. This time I'm going to track x, and I'm going to change the marker here. Just a second. Okay, for the marker, I'm going to use a vertical line instead of just a little diamond, just to emphasize the nature of the motion. Let's run that. And notice how the horizontal position, let's just show all of those right now, all steps. The horizontal position is changing with uniform increments in uniform amounts of time. And if I look at the graph, it looks like a straight line. So here we have an example of a linear equation spelling out the horizontal motion. At the same time, we have a quadratic equation describing the vertical motion. Let's look at this in the data tool. Okay, here is the vertical. This is y versus time. And so what I want is to fit a parabola to this. So down here, fit name, I'm going to say parabola. And if I select some data here near the top of the curve, if I fit the parabola to those data points, it fits all of these pretty nicely. All right. So this is indicating that the vertical motion up and down is described by a quadratic equation. Let's look at the horizontal motion now. Okay, so if let's make this a line this time instead of a parabola. If I fit a line to this data, notice that it's a good fit all the way until right toward the end, because there is a little bit of horizontal force, namely air resistance. So we can see the mathematics is an idealization of the physical reality. So it very well describes the horizontal motion, but also shows the limitations that, yes, there is a horizontal force that ultimately you have to take into account if you're going to have high precision measurements. One of the topics that comes up in several different math courses should show up in geometry sometimes, but it'll definitely show up in Algebra 2, is conic sections. And in particular, this is an ellipse, and these are fun to play with. They're sufficiently fun to play with that you may not even get the question of when we ever going to use this, because who cares, they're just fun. Notice this construction process for getting an ellipse. If I change the parameters just slightly, it transforms this ellipse into something called a hyperbola. Now this is getting weird, so still you can trace out this hyperbola, and it's like both branches are really part of the same overall curve. And again, you study this in Algebra 2, and that gets to the point where you say, whoa, where does this ever show up? Well, it turns out hyperbolas show up in physics as well. Let's look at an example. Okay, this is a ripple tank, and what we have are two little points that go up and down and create circular ripples coming out from those 2 points, and then they overlap. And the pattern where they overlap is called an interference pattern, and this is common for any kind of waves. We're just using water ripples as a way of visualizing this. Here's a GeoGebra simulation of the same kind of an effect. Notice that there are these gray lines that come radiating out from between the 2 point sources, and those are where the ripples from one source cancel out with the ripples from the other. And so you get whole patterns that emerge out of there that are totally canceling all the time. So those are called lines of nodes. If you follow those curves, it turns out they're hyperbolas. This is an example of where what you learn about hyperbolas from math has a direct relation to studying wave interference. Okay, let's move on to some trigonometry. And what I'm starting with here is just the basic definition of sine and cosine, at least the unit circle definitions, which are a little bit more useful than just looking at a triangle. Initially, people just associate trigonometry with triangles. But here's a triangle, but it's inscribed in a circle. And as long as it's a unit circle, that's a circle whose radius is 1, we have some nice simple ways to visualize sine and cosine. So this is all what would happen within a math class. So if this length is 1, the radius, then this distance is the sine of the angle. So right now it says that angle is 47.9 something, and this would be the sine of that. And you can poke it into a calculator and come up with this. Or you can just do it on the graph and read off from the squares here. 0.742, well here's 0.6, here's 0.8, and you could estimate that that's about 0.742, and so forth. So that's the sine of your angle. And here's your cosine. So you can see these very directly. It's not a lot of memorization. So at least that's a good way to get started with the definitions for these things, rather than memorizing all the ratios. Memorizing the ratios is useful for some things, but here you go. So you might say, well, what if I have a situation where this is not a unit radius? What if I have a distance out here that's 5? Well, everything's 5 times as big. So if that's 5, that's 5 times the cosine. This is 5 times the sine. And so you still are good to go. Okay, here I'm just taking the sine function. And what I'm doing is, as I move this point to the right, what I'm doing is I'm wrapping around this unit circle. And so as we just now saw, that's the sine of the angle. But as I think of this as unwrapping just think of this as tape. And I unwrap the tape to the side, then the distance along this line is the distance along the curve here. Okay. And so if I go all the way over to here, we're back down to 180 degrees. And if I'm down here, that's 270, here's 360, and so forth, and I just keep going. So notice that sines and cosines are useful for something more than just solving triangles. And in fact, it's useful for more than just working with the circle, but we can also deal with something that looks a lot like oscillations and waves and things like that. So that's actually one of the big areas where trigonometry enters into physics, is representing oscillations, vibrations, waves, things like that. Okay, here I have a mass that's hanging on a spring, and when I let it go, it's going to oscillate. That's called simple harmonic motion. Let's watch this. And notice that it's being tracked over here as it goes up and down. And it's clear just from looking at this little graph here that it's a very good approximation to sinusoidal motion. The rate at which it's oscillating, in other words, how frequently it goes up and down, by the way, frequently and frequency come from the same word, depends on how much mass and how stiff the spring is. So that's the way you have to model this motion. And so then you can figure out the period of the motion based on the spring constant of the spring and the mass. Okay, here's another situation where we can use sinusoidal motion to model what's happening. This is a pendulum, and what I've done is I've chosen a particular length for the string, and it turns out the amount of mass we put on it doesn't matter at all. It just has to do with the length of the string and the fact that we're in a gravitational field. Notice that we're oscillating in what appears to be perfectly sinusoidal motion. But this is a little deceiving. It turns out if we make larger swings, the deviation from perfect sinusoidal motion becomes more apparent. So what we can say here is that we can use sinusoidal motion to model what's going on to a high degree of approximation that basically is valid for small oscillations. Okay, another use of sinusoidal functions to analyze things in physics, you might anticipate this one, but it's looking at sound. So here what I have done is I've played a recorder. I have a little plastic recorder. I am not a musician, but I made some notes with this thing. And so let's look at this and analyze it. I'm using software called Audacity. It's a free download. It's a good program. Go get it. And I'm just going to play one of these notes here. And let's see what it sounds like. Not very steady and whatever, but there you hear the note. And let's zoom in. Let's see what this looks like. If I go way in till I can see the individual waves, it looks very much like a sinusoidal function. However, this is not a pure sinusoid, which we can show if I, let's take a section of this, and let's go up here to Analyze, and go to Plot Spectrum. And what we're seeing here is these are frequencies down here at the base, and this is telling how much of that tone is each of these frequencies. And notice that I have a whole series of the main tone here that we're hearing, but then these are overtones. So what we're actually seeing here is a combination of waves at different frequencies, all piled on top of each other, and it looks pretty much like a sinusoid. But notice the shape is not exactly rounded perfectly and so forth. That's because it's not. It's several waves added together. Okay, so here's another example of where what we know about trig functions, sinusoidal functions in particular, enable us to get a lot of information about the sound that we're making. A synthesizer is an example of using a mathematically generated function and then feeding that through speakers and so forth, and you can get sounds that are created to take on particular tones. And if I combine the sounds from there, just like I noticed that this is a combination of tones, if I made the same combination of tones just by creating them and adding them together, it would sound like a recorder. Or I could make a synthesizer sound like a violin, and so forth. So analyzing sound and synthesizing sound are all part of this process. And you couldn't do it without trig. I want to close with one last comment, really. We have been talking about a problem like where you take position as a function of time. And if you take a very simple situation where you have a straight line graph here, we can find the slope, and we said that slope is going to give you the velocity. Well, what happens if you plot velocity versus time? What if I figured out the velocity everywhere along the path and make that the graph here? In fact, what if instead of having such a simple situation, what if we have some more general kind of a graph, like, something like that? Okay, if that's our position, so we're moving forward and then stationary and then moving forward again and so forth. If I found the velocity at each point, notice the velocity here is not very great. Here the velocity is faster, and here it's faster. I can find the slope along the curve, and if I make a table and come up with the velocity everywhere along this path, I can plot that velocity as a function of time. And I'll come up with some other kind of a graph. I'm not even trying to make this realistic here in the terms of the appearance. It turns out that if I find the slope along a velocity time graph, I get the acceleration. And so if I do that everywhere along the curve, I can come up with a third graph, acceleration, and I can plot that as a function of time. Okay? So we have these three variables: position, velocity, and acceleration. And they're in a particular relationship with each other. Namely, to go from here to here, we have to find the slope everywhere along the curve and then replot it, and you get this graph. And do it again. take the slope everywhere along this curve, replot it, and you get this graph. And then we might want to come backwards. If I start with the acceleration data, can I recover the velocity data, and from there the position data? Well, doing this for very simple curves like parabolas and straight lines and so forth is something we can do in a high school level non-calculus physics class. But the process we're doing is at the very heart of the meaning of calculus. This process here has a name. It's called differentiation. And that's one of the things you learn how to do in calculus. Taking a curve, finding the slope everywhere along the curve, which allows us to transform this information into this information, and then again, this into this. So from position, we can find the velocity and we can find the acceleration. Or if we know the acceleration as a function of time, we can go backwards. This process is called integration. I haven't even written these down. So differentiation and integration are inverse operations of each other, and that is the essence of calculus. This kind of problem is, it turns out, a pretty big deal. And the first time you ever encounter this would be in a high school physics course. So at that point, this connection between math and physics is more than just sort of an entertaining sideshow. At this point, it really is at the heart of understanding the concepts. So I really highly recommend, if you're about to go into calculus, that you consider taking physics along the way, because it'll make the whole process much more meaningful. So that's all I wanted to say just to close out. This is actually an important message. If you're on that brink of getting ready to take calculus, be sure you take physics either ahead of time or at least along with it. Because if you take calculus and you don't have any physics, you're in for a lot of abstraction and you may wonder what it's all about, really. So there you go. All right, I hope this was not too painful to sit through this session. I enjoyed putting this together, and hopefully you got something out of it. So I'll be here for Q&A.